did bring it in for one.
Okay, so we're still doing functions of multiple variables. For the most part, as you can see, we stick with two variables when we don't have to go deep into this notation. Just for now. So the last topic is linear approximations. As you can see, they're applicable. They start at the end of calculus 1 or so, and then in calculus 2 they also reappear. The definition is given first implicitly as the formula, then it is discovered to be a specific linear function with its slope being the derivative. And then it is also connected with the Taylor polynomial, this being simply the degree 1 Taylor polynomial. And then now it is up to us to take it to the next level, to dimension 2 is higher. As you can see, we reproduce the same formula, so the difference of the two functions, the linear function candidate divided by the magnitude of the run. So the run on the xy plane from that point of interest A, B, and that is the denominator. That's the run, and the rise will be literally the rise of the rise of the that plane L over the actual curve. Okay, so it's not really a run in the sense that we have had. So then we ended up with this theorem that says that this linear function L, we know how they are represented in this fashion. Both of the numbers are, both of the slopes are, or coefficients of x and y are the partial derivatives of the function. It's all under the assumption that the function is differentiable to begin with. So we do not assume anything that about that. We just say that in the beginning of the theorem, we say that the function is differentiable. Okay, so differentiable, that to begin with it has a tangent plane, which is kind of not redundant, but rather circular in a way. So we say that there is a tangent plane, and then we go on to say what that plane is. Okay, that's the way we can interpret this. Okay, so some applications to follow. Partial differentiation in how to do it to follow. We're just proving quickly the theorem itself. So that's our function. And then the assumption of differentiability is right here. The assumption of differentiability is here, and then by the theorem about the limit of one variable at a time. So in other words, you can just evaluate this limit any way you like. The answer will be the same, no matter how you approach the point. So that expression here that we have here allows us to approach, or requires us to approach the point in all possible ways, straight line or otherwise, or curve. But once we establish we assume that it is the case, then we could pick anyone we like, and we like to go along the x-axis. Okay, so if that is our choice, and we do, and then suddenly everything simplifies because x approaching A, so x approaching A, and y is fixed at B. Okay, so y is fixed at B, so some of the terms disappear, the denominator simplifies significantly, and I'm left with this in the numerator, which is really not a big challenge now. Okay, so let's from the right and from the left. So this limit is 0, and if I separate it, I split it into 2. What did I do okay, limit. So this will be f of. Why is it the wrong way? Lxy. It should be the other way around, but that's f of xy. Okay, plus m x minus a, x minus a, x minus a. Okay, this thing is equal to 0. That is given. What are we trying to establish? And we're trying to establish that, we're trying to demonstrate that m is in fact the derivative of the partial derivative. In other words, it is in fact, I'm sorry, this is not xy, but xb over here, xb. So once again, y is fixed at b, and we're approaching along the y-axis. So then indeed everything has been fixed on the y-axis, that is, and only along the x-axis we have something changing. And then I am concluding here that what am I concluding here? I am concluding then that m is equal to the limit of f of ab minus f of xb. Yeah, that's actually the wrong way. So it will be a minus x over here, and x goes to a. Okay, which is the partial derivative. So it is d f dx ab. Okay, so the partial derivative with respect to x. So there's part 2. There's some details to be worked out here, but unfortunately we just don't have enough time for that. So we'll go on to just use this theorem as necessary. The differentiability condition is harsh, so that limit has to be equal to 0. And so instead, there are indirect ways to establish that. So that's all. Okay, so let's take another look at our formula for the our theorem and our formula of the linear approximation right here. Okay, and then we can certainly ask ourselves. Let me write it out again. We can ask ourselves, so L of x is equal to L of xy is equal to f of ab plus m x minus a plus y plus a plus m y minus b. Okay, so that is a linear approximation of the function with m is equal to the partial derivative with respect to x at that point, and n is a partial derivative with respect to y at that point. Okay, so that's a linear approximation at that point. So I will dwell on the fixed point situation for a while, just like it. I hope you did in calculus 1. So function derivative as a rate, instantaneous rate of change of a function at one point. Then once that has been learned, well, you proceed to derivative as a function. So then it might seem to become easy. You differentiate at every point, and you suddenly have the whole derivative as a function. Well, it is a misleadingly simple, but the reality is quite complex, especially in dimension 2. So let's stick with 1 point at a time. Differentiable at 1 point, linear approximation at 1 point, rather than just all of the tangents. Imagining the surface with all the tangent planes attached to it. So it is already a challenge to begin with. So in dimension 1, at least you can think of that's the representation of the derivative of the function with the tangent lines attached all over the place. So that's the representation of the derivative as a function. With dimension 2, you have a surface with all the tangent planes attached. Okay, that is still a challenge. So let's stick with the approximation for now. But there is a way to make life easier. Well, you remember how we can simplify this expression. Remember representations of planes?
Just multiply through by the constants and add all the constants?
No, that's not what I meant. Okay, well, how about let's make it more complicated, and that may help you to remember. What if I have a third variable? If I have a third variable, there will be plus k z minus c. things become more and more complicated. The k will be the other derivative of the function of 3 variables at that point, which is now really hard to visualize at all because the function now, the graph of the function lives in the 4-dimensional space, so visualizations are out of the question, but the algebra suggests itself as we already did it before. What do we do with this expression?
We turn it into the dot product.
The dot product, right? So that would be very helpful. So it will be simply f of a b c plus vector. I think I called it m dot x minus a. Okay, where m is made of partial derivatives, d of dx, d of dy, d of dz at a, b, c. X is equal naturally a, b, c, the point a, b, c, and x is equal to x, y, z, and a is equal to a, b, c. X, y, z, the variable point. A is the fixed point that we are studying, a, b, c, and then the whole representation of the linear approximation of the function becomes very compact. So it's the point plus what? Plus the increment of the independent variable of the input, multiplied by some numbers which is made of the slopes of the, multiplied by a vector which is made of the slopes, as you see here, of that tangent plane in the 3 directions of the 3 axes. This vector is called the gradient. The gradient of f at a, b, c. Okay, so it is simply the vector with 3 coordinates, each of which is the partial derivative of the function evaluated at that point. Naturally, if you have a 2-dimensional situation, then you have only, the vector will have 2 components. Okay, so remember that it not only, if you remember the meaning of the partial derivative, that's not hard to remember with the meaning of the gradient. It simply gives you the slopes in the directions of these 3 axes, but also the previously discussed idea was that indirectly it gives you, let me put it this way, 1 d of dx, d of dy, let's say 2-dimensional case, and 1, what is this? This is a vector perpendicular to the tangent plane, or a normal vector of the plane. Remember, so it is made of the 2 slopes, the 3 slopes along all of the 3 axes. In this particular case, if we're talking about the 2-dimensional plane plus 3-dimensional z, we could just put vertically 1. And that will be the normal vector of our plane. So that's what's hiding behind this this representation. So as you can see, the algebra helps us to make everything compact, and every letter has a lot of stuff behind it. The notation is either gradient, grad of f, or there are some others that we'll discuss later. So the partial differentiation of the gradient is still to be discussed. I want to do some. I want to do the actual linear approximation so that it would kind of sink in. And starting with the problem that that you see in calculus 1. Here somewhere. Okay. So just to refresh your memory, I'll. Okay. Okay, so linear approximations again. By the way, what is a linear approximation of a parametric curve?
Just the vector whose components.
Well, not a vector. I mean, it's got to be a function. So,
Okay.
with the same variable. So you're trying to say tangent vector, but it's actually tangent line. Okay, so tangent line that we know how to find by finding tangent vector first will give us linear approximation. So it's still the idea is still applicable to parametric curves, and now we're talking about a linear approximation of function of several variables. And but let's go to dimension one, back to dimension one, and the question might be like stated like this: approximate square root of 1.1. Does this seem familiar? Okay. So as you can see, there is no mentioning of function, there is no mentioning of a linear or otherwise approximation, just you have to approximate 1.1 without a calculator, naturally. So, or you can think of it about it, devise a calculator that would compute a square root of 1.1, or in general square roots. So because the calculators, I mean the computers are built in such a way they can only carry out very simple basic operations such as say addition, and everything else is built on top of it, and not easily. So if we want to then to teach the computer to do more complex computations such as square root, we do linear approximations. That's what's inside the calculator. Okay. So what do we do?
It's one where it's like in between the square root of 1 and square root of
Well,
4 or something.
sure, okay, so that's fair enough. So it's between a square root of 1.1 will be between the square root of 1, which is 1, and square root of, say,
Is it 4? It's just easy one.
yeah,
too big, though.
exactly. Yes, you can see it's pretty big. So square 2, which is square root of 4. Okay, so that's a pretty crude one, and in fact, it is actually a better way to understand approximation than anything else that you may see somewhere, because even though it is very crude approximation, but you actually provide us with an interval. You know that the true number square root of 1.1 lies somewhere on the interval 1, 2. So even though you don't know accurately the truth, you know the truth is true. So that's the interval, and it is there. So between 1 and 2, it's here somewhere. Okay. So if, for example, you say square root of 1.1, well, it looks like 1.2. Okay. So even though it might be a better approximation than the whole interval, it actually does not tell you what. It does not tell you how close you are to the truth. Okay. So whatever we're going to come up with that approximation, it will be incomplete in that sense. It will not have give us the confidence to know where it is exactly. So that's why every approximation theorem comes with error estimate. Remember error estimate in Taylor series theory. So it's pretty much the remainder of the series. There's an estimate for it. So we're not going to do it now, but that's to be remembered that always if there's an approximation, there is also a statement about how good your approximation is. Okay, so and then it will look something like that, except the interval will be smaller than that. Okay, so the most natural approximation, degree 0, if you like, would be simply 1. You start with 1.1, find the nearest one number that is easily to evaluate the square root of, and then that's your answer. Square root of 1 is 1. That is a very easy approximation. That is simply you approximate your squared function with constant function. That's what it is. So if this is 1, I replace the function with that curvy function with y equal 1. So it's a constant function. And this time, however, the approximation that we carry out in calculus would be better. We're replacing it with a linear function, and specifically the tangent one. Degree 1, I have to replace, I have to do more than that. So what do? We use that theorem about linear approximation of one variable from calculus 1 or 2, and then we will proceed to two variables. So the linear approximation is just what we did just recently is L of x is equal to f of a plus f prime of a, x minus a, Okay, that's a linear approximation where what do we have here? L is to be found. Naturally, f of x is our function square root of x, which we're trying to approximate around that particular point, being 1. So it is okay to choose 1 as the nearest point and do approximation there, because this is where we are. We're not too far off x equal 1. So that's fine, and the derivative is to be computed still. So f prime of x is 1 over 2 square root of x, and f prime of a then is equal to 1 half. Okay, so in other words, we already have my linear function. L of x is equal to f of a is equal to 1. I should have done here. Square root of 1 is equal to 1. So it will be 1 plus 1 half x minus 1. Okay, so that is the linear approximation function, which I have right here. Okay, so it's tangent line to our curve at 1. We are not trying to find naturally tangent line at 1.1, because we don't know anything about that location. We pick a location we know everything about, the location where our computations can be carried out by hand or by a computer with kind of unsophisticated computer. So as you can see, differentiation, we could differentiate ahead of time. Suppose we're planning to devise a computer that does square. Okay, so what do? We compute derivative ahead of time by hand. Okay, and then so that function presumably exists in our ability to compute it. But then it's still not as simple to understand what's happening, because it's the derivative itself is complicated to begin with. So then we pre-compute our function as well as our derivative at several locations, strategically distributed, and then along these locations we carry out this what we're just about to do. We replace our function with its linear approximation, because we know the value of the function, we know the value of the derivative, pre-computed ahead of time, and therefore we have a bunch of those tangent lines, not all of them, because we only have a few that we were able to evaluate. In this particular case, I would do 1, then the next one doesn't have to be 2 or rather 4, but rather you can take what 1.44, for example, 1.21 or something like that. The one that you know answer for. So it is possible to have plenty of tangent lines pre-computed. But let's do just one. So L of x is this function, and then it really remains very little work. I just plug in 1.1. So it will be 1 plus 1 half, 1.1 minus 1, 1 plus 1 half, 0.1, or 1.05. Right? 5? Yeah. Okay, so that's the approximation. Okay, so moving on to the two variables. The same procedure. In fact, I'm going to choose a function that is somewhat similar. So dimension 2. And words will be approximate square root of 1.1 multiplied by a cubic root of 0.9. Okay, so it would be smart, but ultimately mistaken idea to just split it into two and do the evaluation, estimate this, and then estimate that, as if it's each time it's one function, then multiply. Okay, so I mean, we just did this we just did. We can certainly carry out this number 2 as well with no difficulty, except it will be cubic root. So it's in that sense it's really uncomplicated. It's a good idea and it can be done, but we have more than that. We now have more than that information. With our approximation will be not with 2 tangent lines, which is pretty much what it would amount to, but rather with a whole tangent plane. And there is a difference there. Okay, so let's carry it out. Our linear approximation is L of xy is f of ab plus f partial derivative df dx ab x minus a plus d of dy, y minus b, okay, with f of xy is our function, so it will be square root of x cubic root of y. Okay, so this is the function we're approximating. And then my AB is 1, 1. It makes sense, right? For point 1.1, I'm choosing the nearest easy point 1, and same for point 1, even though they're in different directions, but point 1, 1 is fine, okay? Then we're going to need the partial derivatives. So well, let me compute the partial derivatives. So df, I already have my d of dx, which is, where is that? 1 over 2 square root of x times cubic root of y, okay? Then I plug in 1, 1, and I end up with d of dx at AB, that the coefficient of our linear approximation is going to be, plugging 1, 1, I'll have simply 1/2, right? Okay, now d of uy is, I am differentiating, I'm leaving square root of x alone, I'm differentiating with respect to y. What's the derivative of cubic root of y? So what we're doing is that's partial differentiation for you, ignoring everything, well, rather thinking about the other variable as if it is constant, and differentiate what's left. So we are left with y cubed, and that's what we're differentiating. So square root of x serves like a coefficient. We pull it out of differentiation with respect to y, and we're left with the need to differentiate cubic root of y, which is simply the power of
Negative 2/3.
1/3. 1/3, cubic root 1/3, and when you differentiate, you're going to get what's the power?
Negative 2.
Negative 2/3. So it will be y over power 2/3 with coefficient
3.
1/3. So 1/3, differentiate 1/3, and then subtract 1/3 minus 1 gives you 2/3 in the denominator. Okay, so then my derivative at particular point, so once again, we're not using the whole derivative, but just one point, it will give me 1/3. So that pretty much it. I'm ready to write my approximation. Lxy is equal to, the value of the function is still 1. The first partial derivative gives me the slope of 1/2 x minus 1. The next one 1/3 y minus 1. And well, that's it. As you can see, that certainly is quite a simple function. And now all remains just to plug in 1.1.9, the two different variables that I'm plugging into my function. So it's 1.1 times cubic root of 0.9 is approximately equal to L of 1.1, comma 0.9. Okay, so 1 plus 1/2. Once again, that part is repeated. So it will be 0.1, 1.1 minus 1, 1/3, 0.9 minus 1. Okay, so what do we end up with is, once again, this will be 0.05, and this will be negative 0.03. Okay? You can leave it like this, or you can write it, or you can write it as 1.08333. Okay? So once again, approximation is not this of a function's variables. It's not as if you combine two approximations with respect to each of the variables in some weird way, but rather you approximate the whole thing. The tangent plane is made of those two tangent lines, but it's not predictably located with respect to those two planes. So these are two lines, and they generate, they produce that tangent plane. Okay, so that's how we do the linear approximations. Okay, so once again, the part that's missing is the part about how good our approximation is. So we can tell this is a good approximation, but how close is it? We know this is not exact. So if you think about this, it's almost all useless information. All we know that this is it is an approximation. Somebody told us it's an approximation, but where is the true number? So because if you don't know how close you are to the truth, you're not confident about using this number. If you do, then you can trace your error on and see if that error, as it may have or has happened many times, propagates into something unacceptable. Because small error subjected to algebraic operations such as, say, multiplication might produce a magnitude of error that is you cannot anticipate ahead of time. So if you don't have that error estimate, implicit estimate of error, you don't know where you're going to end up. So that part that's a caveat about approximations, and this approximation in particular. There is so if you need, you look up the Taylor approximations, even though usually they do not mention the two-dimensional situation, but it's a separate, entirely separate study, not separate, but rather next level of study would be numerical analysis of how good all those approximations that we do, how well they work in reality. So all of these infinitely accurate things that we have, in reality they can be only approximated, and then how good those approximations are is the subject of the study. Okay, so once again, the gradient of a different of any function, say, z of any function of two variables. So we do not require it to be differentiable. In order to define the gradient, all you need is partial derivatives. So gradient of f at point AB is defined to be this vector d of dx, AB, d of dy, AB. Okay. So carefully, I'm going to put here something that you normally is not being used, but it's certainly worth remembering, worth keeping in mind. What's the meaning of the gradient? It is an operation carried out on the function, not on the point AB. So you carry out you take the function as is, as a function that varies with respect to x and y, compute the partial derivatives, combine them into, and then evaluate those two at these particular location AB. So in other words, without those green parentheses, it might appear that you take f of AB, which is a number, and then there's some kind of gradient of that. No, it is a gradient is the operation on f just as f prime. Okay, just as f prime, or df dx, say AA. Okay, so df dx, then this is good notation, and this is bad notation, df of A dx. So once again, it might appear with this notation that what you're differentiating is f of A, which is a number. Okay, so no, you're differentiating the function, such as here, and then only evaluate that at the point. So the big deal about it is primarily that this is ultimately the derivative. So it's just a word that has been used traditionally in the gradient of the going way back. But if you want one derivative, it is the gradient. So it is a vector. It is a vector of the appropriate dimension. So you can certainly imagine that if you have a function of n variables, so f of x1, xn, so then it produces the gradient of f with the same variable, say a1, an, And what do? You differentiate f with respect to each of these variables, creating then a big vector
It's-
with n variables, with n components. What?
Sorry. I was just thinking, it seems weird that we would call that d derivative when it can
Yeah.
exist even when the function isn't differentiable there. Is that-
No, fair enough. Yeah, so that you would say it is the derivative when f is differentiable. I would agree with that. When it is not differentiable, it's really it's hard to talk about derivative to begin with. The derivative. So you probably are better off really not thinking about the space of inputs as anything that is combined together, but rather you're looking at x and y in an entirely separate way, and then the issue of kind of an omnidirectional derivative does not appear. So you only look at the being this location being approached from one direction or the other, from along x or along y, period. And you don't think about this one, you don't think about those ones, and then you might be okay. And the examples that we had yesterday about that nasty function, it's exactly like that. So it's as long as partial derivatives are concerned, there is no problem. Those derivatives are zeros. In fact, let me make a simpler picture of that exact example. Not that example, but it just looks slightly simpler, I think. There's no formula, but it's easy to visualize, I think. So it's flat. It is flat. The three quarters of the plane are flat, are zeros. So this is pretty much the whole graph. So these are the x's, and my graph looks like this. On these three quarters, and then there's a drop here. This is where the cliff is. It goes vertically here, right under the origin, and then we are kind of going away in a angle away, but not 90 degrees. Okay, so the 90 degrees, these continues on like this, parallel to x and y axes. Okay, and then this is, I build the rest of the graph like this. So these are sloped. Okay, so the point here is to first of all indicate that how simple everything is up there on that plane, quarter of the plane. Everything is constant, totally zero. Certainly partial derivatives are all zeros as well. But there is one direction in which there is a drop right here. That's a vertical drop. But one single location with a drop. Nothing bad happening here to the left or to the right of it. Those are naturally sloped, not infinite slopes. Okay, so that's an example of a non-differentiable function, even though it is actually differentiable at every other location. Okay, so that would be what can happen to functions of two variables or higher, is that it is well behaved at every single point, with one exception where it does not. So the derivative, if it is differentiable, differentiable means that there is a linear approximation, which means that there is a tangent plane, and that the slopes of that tangent plane gives you the gradient, or the derivative as well. So the big warning here is if we probably you haven't made that connection yet, but still you probably will. And the connection is that it seems that it's very similar to parametric curves. Okay, so the derivative, if we are to speak in terms of derivative, the derivative of a parametric curve is a vector. So this is the derivative. So say this is f prime. If we have here, say, x equal f prime of t, then at every location there is a vector, and that vector we have called the derivative. What else, right? So it's if it is in Rn, right? The curve is in Rn, then the vector is also in Rn. Okay, so and then we are in a totally different situation, seemingly, right? So we have functions of many variables. So well, let's say R2, just to keep it simple. R2. Suppose we're talking about a plane curve, and then the two-dimensional vector is its derivative. And then we produce the same result for functions of two variables. Also, the the derivative appears to be a vector, and that's it. I cannot really. I just giving you a warning. So it's not the same type of vector. I cannot say more than that, but it just the analogy breaks down. Eventually, we'll see how that analogy doesn't work. But certainly, you can feel that after all, the relation between functions of variables and plane curves is really very remote. There is no overlap, or rather, there is no overlap, really. Yeah, there is no overlap. So that's why certainly when the derivative produces something that seems similar, it's probably like a coincidence or something like that. Okay, so partial derivatives, just a few examples that you get some of that in your online homework, as well as maybe next one too. It is a skill that you have to have just as much a skill that you have just differentiation from calculus 1. So so that's a deserved a special name, so it's called partial differentiation. And just as in calculus 1, it is an algebraic scale, which you do with your hands. Whether or not there is some geometry behind it, you got to do it regardless of whether you see it or not. And so the geometric meaning is still the same. And you can demonstrate it for dimension two variables. You cut your surface with a plane parallel to one of the two variables. So in this particular case, I'm talking about, say, I do this. I cut this piece from my surface, and then treat it as a function of one variable, and then this surface has it changes. Okay, so that's the slope of this is df dx ab. Okay, so like this. So that's a point AB over here. That's all right. So geometry is okay. We can and should bring it in when we can. We cannot, however, once we go to beyond two variables, the geometry kind of fades away, and so we have to do a pure algebra. Okay. Okay. So differentiation is the rules are the same. But the other variable is treated as a constant. Not treated, it is a constant. So as I just did say, x squared y cubed, if I am to differentiate it with respect to x, then y cubed is a constant. So df dx, let me just use the parentheses like this. So just df dx x squared y cubed. Y cubed is a constant. I don't need to use the product rule. That's the product rule. There is nothing wrong with the product rule. It will still work, but it is better to treat as a constant. So I simply factor y cubed out, and I'm left with, if I can. Sometimes I cannot. And I end up with this. So it will be y cubed 2x. Okay? Similarly, if I do differentiation with respect to y, now this time the other one, you have to switch in your head from what is being variable, what is constant, what is the variable. So now x squared is my constant. Okay? So it is x squared 3y squared. Okay, so so that's an example of when you have what we end up applying is the constant multiple rule. Okay, in either case you apply the constant multiple rule because it is constant. Y is a constant when you differentiate with respect to x and vice versa. Similar idea applies to what if we have addition. It's even simpler because under addition, when we treat the other term as a constant, it simply disappears by the sum rule. So I have simply 2x. find the summary once again. Okay, so it's really uncomplicated, but the point of view is important. Like I said, you treat the other variable as if it's a constant. It is very typical in many applications of, say, physics, when there's a bunch of variables involved, and some of them are maybe variable, maybe not. But if you are, it doesn't matter, because you are interested in what if the other parameters fix. Okay, and then what is the effect of the original parameter? So one, in fact, I don't know if this helps. It is, you can compare these two related rates, which looks very similar, and I don't want to any confusion here, because we are talking now about unrelated rates. So you might remember something like x squared y cubed is equal to 1, and then we just did this, x squared plus y cubed, and you could differentiate with respect to the either one or the other, and we already have those answers over there, y cubed 2x and x cubed, so x cubed, x squared 3y squared. Okay, so and related rates, remember related rates is the presumption is that this is like a relation, implicit relation between x and y, and then you differentiate how? You treat as if y depends on x. It is the exact opposite of what we're doing right now. So let me carry out. So if I do differentiation with respect to x, observe the straight x. On the right natural I have 0. Okay, so remind me how I differentiate this on left. Just to remind you what you're not supposed to do now, if it helps. Okay, so how do we differentiate this on left? So related rates, so you have the x and y are related to each other. In fact, we think of as if y depends on x, and we differentiate in that manner. So to differentiate this expression, I apply the product rule, and so I have 2xy cubed. The first term, and the second term is x squared times what?
3y squared dy dx.
dy dx. That's right. So that term reveals the idea that the two variables are related to each other. On the right, they are not related. Why? Because they're literally called independent variables. X and y are independent variables, therefore they are not related to each other, therefore there can be anything like this. Okay? So we'll talk more about that